Welcome once again to the lecture number 18 of the deep learning course. In this session, we are going to talk about that how deep learning is helping to solve the computer vision problem. So this part is very important, and after that, we are actually going directly to see the important models that are going to come and that are there proposed into the deep learning domain. So I would start this discussion by showing you this block diagram. And this block diagram, I think I have already given you some hint and talked to you sometime that if you want to develop any kind of system that can perform some tasks, so some of the things that generally you need to do. For example, if you want to perform a computer vision kind of task, so this is a kind of general pipeline that you have to go through. So what is that? So let me take some examples such as let's assume that there is an image, and in that image there could be cat or dog, and you want to tell that whether there is cat or whether there is a dog. So it is a classification problem. Here input is going to be an image, and then the first part comes in most of the system. The first part should be quality check. Whatever input you are going to get, is it the right input that you should take it forward, uh, or you should neglect this and go for the another acquisition of the same thing. Sometime the acquisition that actually come to you, for example, if you here you have deployed a kind of camera to find out something, some input is going to be given over here, so it may drop some of the frame if there is some occlusion or any kind of problem. So the quality check is there that actually try to find out whether the thing that has input is of good quality. If it is not, then the recapture of the same thing happens. If everything is fine, then you send it for the enhancement. Enhancement is a very important part, and it is not only the thing that you are going to improve the quality of the input, but sometime you to do the overall improvement into your system, you do some kind of changes over here so that the time required over here can be reduced, or the things which you are actually having here are better suited for the things which can be done at the later point of time. uh, for example, I can give you an example where just try to understand that. Let's assume that so, uh, so let me tell you that there is something called the four slab machine. Okay, so four slab machine is something, a fingerprint acquisition system, where you are going to put it has a kind of surface, and you are going to put your finger on the surface. So for all the four fingers you are going to put on that. So ultimately, essentially, what I wanted to tell, that this particular device is like that. Let me draw the 3D dimension, 3D thing. So this is a kind of device, and on this particular surface, on its main surface, you are going to put your hand. So putting your hand means what? That you are going to put all your four fingers over here, and you are going to push that. So the system actually, if you see that this particular part from the top view, you see that this kind of image you are going to acquire. So some kind of this kind of some this kind of image you are going to acquire. Okay, so you know that your finger has three part, but if you look closely, so fingerprint is only available on the top part of each of your finger. So you know that fingerprint is actually, if you have a finger, so there are some ridges, so they are going to bifurcate, or they are going to go from one place to another. So this kind of structure is there. If you see the below part of your finger, it is not like that. The things are something like this. So here there is no fingerprint. Fingerprint is only acquired from the top part. So if you have a four slab fingerprint acquisition system, your objective would be to give me the fingerprint, because if you do the matching of the fingerprint, you need to find out this particular portion, and when you cut this part, and then individually from one person's four fingers, you are going to match these fingers to the other people's four fingers. So the first part is going to be that you somehow find out that where is the location of this particular finger, and you want to cut that particular part. This particular task, that has a name called the segmentation. You have to do the segmentation. And if you want to do the segmentation, you can think that only what is the XY coordinate. If somebody tells you that what is the top left the corner and provide what is the length and breadth, only these four numbers, you would be able to cut that. Okay, so output, what is the, if you want to do a segmentation task, these four value you have to specify. Once again, not four values, 4 multiplied by 4, because for every finger, with respect to every finger, you are going to tell me these four coordinates, four values. So it is going to the xy coordinate of this particular location, and that what is the length and breadth, and by this you can cut this particular area for all these four fingers. Mostly what happens that if you collect the image, it is going to be of very large size, for example 1080 cross 1080. So this much size image is actually going to be fed. So if you do the processing on this size of image, just see that how many pixels it has. So just for the sake of simplicity, if I say that it is going to be 1000 number of pixel, so you see that there are 100000, these many number of pixels are there which you are going to feed into the system for doing the processing, and after that you are going to get what, 4 multiplied by 4, only 16 numbers you are going to get an output. Just see that, let's assume that we want to do the segmentation. So output is going to be 16 numbers, but you are feeding this much number of the things. And in the same way, you can think that input is going to be, if you want to find out that whether there is a cat and dog, so a a big image you are going to provide to the system, but at the end you are going to get only 0 and 1. So output may have very less things, but input ca- can be sometime be very large. So in this particular scenario, especially for this particular scenario where I'm going to do the segmentation, it would be nice that if you can somehow fasten this method. And one method could be that if I say that, okay, I am going to reduce this particular image size, instead of 10 cross 8, 10 80 cross 1080, I say that 108 cross 108 image I take. How can I take this? In the original image, every 10 pixel going to take that particular pixel, and I'm going to put into the another image. So it would be a very small image as compared to the original one, but if I apply this processing into this thing, and if I come up that looks like that in this small image, here is the location of the xy. So original xy can be just find out by multiplying 10 to the whatever you are going to get from this particular image. Okay, so if you do this kind of thing, that you are going to you have reduced the size of this particular image, what happens that your processing becomes 100 times faster. It's a very good idea it's a very good idea that if you can do on that. So enhancement is actually not only the improving the quality of the thing, so multiple things actually comes into this particular place where you actually are going to improve your system at the later point of time. After that, what is needed, that if you after that you have to find out the right kind of feature which actually define your particular problem. And then again, multiple choices are there for this particular thing also, that surf shift feature, surf feature, orb feature, other features. So multiple kind of features are available. Then you store that thing in your database, because if you have database, you can store over there, or you can fetch something from the database, because if you want to find out that whether he is a cat or dog, so similar kind of images where there was a cat, similar kind of feature when you know that these images are where of the cat images or dog images, you must extract the similar feature and put it into the database so that you can match it and find out that whether new feature is very similar to the cat or dog. Then after that, a decision mechanisms need to be implemented. So we have seen this multiple number of times. So it's ultimately what happens that your system comes out to be that if you say that there is a neural network for this particular part, neural network for this particular part, neural network for this particular part, everything you say that there is a neural network, you put all these things one by one, stack one over other, stack one over other, and you say that I have one single system that is going to work, do my task. Here you are going to provide the input, and here you are going to get the output. So this is a kind of end-to-end learning. Means if you develop the system like this, you say that it is a kind of end-to-end learning. Everything is there. So here only one system is going to give you the output. So this is our understanding that we have done multiple number of time. One more thing that I want to tell, that let's assume that you actually are focusing on a particular a kind of enhancement mechanism. And as I told you that it is a neural network. So if you can change the parameter. So let's assume that the parameter are w. If you change the parameter to w dash, what happens? that a different kind of enhancement would now be applied. It is not the same enhancement that you were actually applying earlier. Okay, and this is very easy for you because changing the parameter is not that very difficult. You just change the parameter and you get the different kind of enhancement. Uh, what do I what actually my objective is, that I want to say that different kind of enhancement 1, enhancement 2, enhancement 3, different kind of enhancement you can apply. Similarly, for the feature extraction part also, you can say that with feature extraction 1, feature extraction 2, feature extraction 3, different kind of feature extraction mechanism you can obtain by changing the value of the weights. Similarly, for the matching also, matcher 1, matcher 2, matcher 3, matcher 4, different kind of matches are possible. And you by yourself can see that this is not a single thing, okay? Because the possibility of the parameter is going to be that you can change is actually very high. So this set is very large, okay? So into the systems, when actually people do the handcrafted based methods, so if they want to develop any kind of, when they want to develop any kind of system, they have to by themselves try to understand that if I am going to use this feature, I have to use this kind of feature enhancement, and I have to use this kind of matching strategy. So all these things the people have one the person have to decide, if they, a programmer have to decide that what is the right way to do that. However, when you put these things into a single unified kind of architecture where you say that everything is actually connected, so they, so the multiple possibilities which were actually earlier, you can see that using this kind of thing, then this feature and this matcher, or you are going to use this feature extractor, this feature and this matcher, or multiple things. So you can see that out of multiple such options, out of multiple such options, everything is being decided over here. What do I mean by this? Sometime let's assume that you come up that looks like that shift is a very good method. Okay, so you say that this is the feature extract, this is a good feature extractor for me. So which is the enhancement is for my kind of problem is going to suit me, I may not be perfectly knowing that. Okay, maybe if I pick this one kind of enhancement, maybe a small change in the shift, this is going to be better for me. Okay, so if you put these thing into this kind of structure, then the advantage that you are going to get is this, that you need not to by yourself specify that which is the enhancement, which is the shift, which is the feature, which is the matching, which is the decision, all these component, what are the actual values of them, you need not to define by yourself. The system based on the input and output decides that what is the loss and try to minimize that loss in a systematic manner so that the loss becomes very less. If the loss is very less, means what, that all these things which are actually put into this particular box, they are all are synchronized and they are working in a unified manner. Make sense? So as we have discussed, there are various choices at the each levels, and when we put all these things into a deep learning pipeline, they are going to give me a better representation, and it is that's why called the end-to-end learning. This is not many of the time very easy, and you know that computer vision is very confusing sometime, because even for the humans, if you don't pay the much attention, you can not find that where is the chicken and where is the dog. You can see that here you can very difficult to find out where is a dog or where is a donut. You can see that intra-class variation, and there is a the difference between the two classes sometimes becomes very faded when you see these kind of images. Can you see this? Okay, see this image where there is an apple or owl. So sometimes and also carefully selected things, don't talk about them, because they can be very very difficult. If we carefully make some of the counter examples, then it would be very difficult for the system to get the right things for that, because you have seen that they are designed in such a way so that they fool the system. Okay, so deep learning is actually an approach that actually try to combine that try to combine a different portion of the different component of the system in such a way so that you can perform the end-to-end learning. This is what we have learned till now. And here our approach is going to be that we are going to use neural network, neurons. Okay. So if you want to do the computer vision, you have to train the system in right way. Okay, you have to show the computer a lot of examples so that the computer becomes very good. Just see a 5-year boy, because if there is a kid of the only 5 years, you can think that he can identify many things. Na? If 5 years, maybe some kid is there, you can ask that what is there. He can tell that this is aeroplane, this is bus, this is truck, this is car. Everything he can tell. Most of the thing he can tell. But do you see that how much examples you have shown to him? Okay, so you know that human can see 25 frames. You know that in general humans have the 25 frames per second. They can see this 25 frames in a second, and if we see more than this, then they becomes confused. So that's why all business of the video actually goes. So in 1 second he sees 25 images, and in the 60 seconds he sees how many? This much. In 1 minute he says these much number of images. If in 24 hours he sees these much many number of, but let's assume that he sleeps for 10 hours, so in 15 hour he sees these many number of images. In 365 days he sees these many number of images, and if the age is only 5 years, so this much number of images he must have seen. Are you right or not? Do you, do you agree with me? Yes or no? Yes or no?
Yes, sir. Yes, sir.
So can you find out this number for me, that what is this big number? 25 into 60 into 15 into 365 into 5. Can anybody do the computation for me, calculation for me? Hmm? What is this number? So this is a very large number. Can anybody write this here? So this is more than, I think this is more than 100 crores of the images. More than 100 crores of the things. 100 crores means how many millions? I think 1 million, 1,000 million images. This becomes 1,000 million images. So around 1,000 million I have shown images I have shown to the system. Okay. Somebody is telling 2.5 million images, I think. Okay. So just try to find out, it's near about 100 crores. So 100 crores is 1,000 million. So this is a very big number. What I wanted to tell, that the humans have actually seen these many number of images. That's why they are performing a kind of reasonably well. But if we wanted to ask from the computer that I have a database of face images, and you want to ask from the system that given somebody else image, can you find out that whether he's the same person or not? Or sometime if you want to feed the image of cat and dog, and you want to expect that the system is also going to do the work better. So how many examples you are showing to the computer? So very less images. Most of the time you say that 10,000 images or 20,000 images. Even very large, if you create a image database of very large, say 1 lakh images, and you show to the system, it becomes very difficult for you to even train sometime. So it is it is not reasonable from the computers to ask something to be done very useful until you show them a enough number of big enough size images, database images. Are you able to see that what I told you, that if you show enough size database to the learning system, then only you can expect that the things are going to be better. So this particular requirement was actually thought by very big researchers into this particular computer science domain, and they have actually collected a database of the images, a very big collection of the database of images, and it was a 14 million images they have collected, and there are various This was collected around 2010. So this was collected around 2010. At that time, using the internet sources, Flickr and other kind of online resources, they have collected these many number of 14 million of images. And then they have asked the community to spend some time and label them. Label them means what? That if one image is there, what is inside that image? So somebody was writing that there is a car, there is a bus, there is a truck, there is a aeroplane, there is a flower, there is whatever, whatnot. There is a banana, there is an apple. So many things that people are trying to write. So they come up with 21,841 categories. So those images have 21,841 categories. So out of these 14 million images, if they people has using the crowdsourcing, they have actually tagged them that what is inside those images. And by this, a big database was created, and then people started solving the computer vision problem. Make sense? The point is this, that if you have very small images, if you have shown very less amount to the amount of images to the system, how can you expect that system is going to be very good? You have to show many images. So a community based data collection was done, and 14 out of 14 million images, where there were more than 21,000 identified categories, this particular database was created. And then they have then the group has actually thrown a challenge. This challenge is called Imagenet large scale visual recognition challenge, and this database was called the Imagenet database. And the challenge was given around 2010 to all the community to come up with anything that actually can give very good accuracy on this particular database. And this was a big database, out of where 14 million images were there. So they thought that it would be not good to give all these things to the community. So they have taken out only one small portion of 1.2 million images, where 50,000 around 50,000 testing images were there. So they showed that using these many 1.2 million images, you try to train your system and show me that how good your system is. Some of the images from this database is here, where you can see that that it's some item which is there, it is shifted. So some you may not be seeing the complete thing. There could be occlusions. And for example, in this particular image, if you try to find out, you can say that there is a lady, there is a boy, there is a scooter, there is a road, there is a car. So multiple things could be possible in a single image. It is possible that there could be multiple things are there, multiple labels are there. This is a very interesting diagram. Okay, this is the very interesting diagram that actually talks about that how the actually community progressed. So you know that many of the handcrafted methods, such as histogram of gradient and local binary pattern, SVM, and different kind of mechanisms people has applied to come up and reduce the error of that particular database. That the testing they have trained on, the try to reduce the error and try to make the very good system out of that. So the fast descriptor coding was actually utilized at this time, when around 2010, and the error of that particular system was 28%. Next year, the people has tried the different kind of methods, such as compressed Fisher vectors into 2011, and they try to improve the system, and the accuracy was such that the error could only reduce by 2%. So all these methods are actually handcrafted method. People actually try to come up with the by their own method, that in this I'm going to see that these are the important part based on my understanding, and then developing right kind of system for that. But development was not very steep. Means people were only able to train to means the error was 26% error is too much. Okay, because it's not going to be accepted system. 26% error means out of every 4 images, 1 image is actually wrongly classified. So this result actually got a sudden increase in 2012, and this is a very interesting area when the people started talking about the deep learning. And there was a paper on LeanIt that was actually called LeanIt that came out around 1998, and this was the paper that actually tried to do the classification of Nist database. And you know that Nist database, what is the Nist database? Can anybody tell? So you know that, on your postcard, when you write your address, there is a place where rectangular boxes are there. In this box you have to write the pin code. Okay, so pin code are the numbers. Somebody has taken all these things and cut as a one by one, and then scanned it and make it the database, and this database called the MNIST database, where it is a integer. All the images are very small size, and they contains a kind of digit. On this database, there was a very influential paper that was proposed around 1998, and this uses something very similar to the modern thing. It was using something very actually it was using CNN. Okay, CNN kind of architectures. But as I told you that at that particular time, around 1998, the things were not stable. Software was not stable. Even the operating system, that Windows was coming with the Windows 98. Then after that, Windows 2000, and you know that these time getting the good software, reliable software was very difficult, and hardware technology was also not that much matured. So even the things were proposed around this thing, but people were not able to use that thing for any kind of productive environment. However, as we have discussed when we were discussing about the development of the deep learning, how the things actually developed. So you have seen that around 2007 or so. So there was some other development has been happened where people were talking about that there are some automated way of finding out the right parameters, and something on the voice based recognition system has actually shown promising result using the deep neural network circuits. So by inspiring to that particular work, LXNet, Alex Krajewski has actually proposed a network that popularly known as LXNet, and it is a 8-layer network that we would see all these architectures in more details in the coming classes. So he have proposed a network that is called the LXNet, and the very important thing is that he was able to train the system in such a way so that the error, which was actually earlier 26%, now actually reduced to 16%. So it was a huge jump um, into the development, and everybody people were everywhere people started talking about that. Now we have a very good system, and we can re uh, trying the things using the neural networks. So this is a very influential paper that actually started once again started all the things which are actually stopped at that particular point, and this very influential paper. Next year, a group of researchers actually came up with the understanding that whatever LXNet had proposed using 8-layer was not optimal. So if he have organized the layers in a different way and using some of the parameter shifting, and such as because ultimately he have to specify that how many filters he have to apply, what is the filter size, all these things. So if you do some kind of changes into that particular network, so it was possible to achieve the reduction till 12%. Okay, so whatever LXNet proposed was a very good, because you can see that from 26 he got 16% accuracy. But next set of researchers actually proposed what in the next year they told that on the same architecture you can improve the accuracy, and now the error can be reduced to 12%. This particular architecture called the ZFnet. We would again see this into the coming classes. Next architecture, okay, ZFnet. So if I ask you that, let's assume that you are into 2013, and you have seen this kind of development. So what would you propose into the next year? Can anybody think that what you can approach, what you can propose into the next year? Once again, so you have seen that LXNet was proposed using 8 layers. ZFNet also has the 8 layers. So what would you do? If you want to improve the system better, what would you do?
Add more
So
layers.
add more layer, because 8, with the 8 layer you can see that this was happening, and you have also seen that using 8 layer, if you improve, means you put the things into better way, your accuracy is reducing like this. Definitely you would like to increase more layers. So this is the another next architecture, VGG, that actually tells that I am going to use the 19 layer, 16 layers. So 19, 16 different kind of layers are possible. So VGG 16 is actually more prominent architecture. You see that. Then so ultimately the objective is to tell you that the next architecture is VGG. Okay. So by increasing the number of layer, what was obvious that the number of the it was going to reduce, and then from the 12 it reduced to 7.6%. Very good architecture. Okay, very good architecture. uh, then what would you do if you have improved to this particular thing? What would you do? What other change you can do? What happens that sometimes what happens that if you increase the number of layers as such, so number of parameter you are going to increase. Okay, if you are increasing number of parameters, then you have to do more processing, and therefore finding out the right kind of weight becomes difficult, because with the more parameter, more processing is needed. Finding out the right parameter becomes difficult. So a simplification was proposed by the Google Linet. And Linet architecture actually is a inception. It has another name called inception. Actually, what it does, it implement a very interesting idea that was proposed way back. So into the deep learning, into the sorry, computer vision domain, 2004 is a very interesting time when David Lowe has proposed a kind of algorithm called shift. Okay, and what is the importance of the shift algorithm is this, that it says, this algorithm says that don't see the things as using only one uh, what I say, that only one image in one perspective. What it says, that if a image is given to you, you change it to the another size, another zoom level, you again change it to the another zoom level, you see the things on the different scales. The term is scale. You see the same thing from the different scales. So if a new image is come, a new dog image is shown to you, so it may not be, the next image may not be the same side dog, it may have the smaller dog image also. So if you see the things into the different scales, and then you learn out of that anything, then you can apply that learning on a single image, and then your learning would be effective. Okay, the same idea was actually applied into the Google Leadnet next year, and however, number of layer was also increased to the 22. So you can see that if I say that instead of using single image, you use multiple images, and you also increase the number of layers, so what happens, that number of parameter again are going to increase, and it becomes very difficult to train the system. But this paper also introduces a very interesting idea, that is called the one by one convolution. It also introduces an idea that is called the one by one convolution. It says that if some data is given to you, if a lot of data is given to you, so you can use this whatever inside across all the different layers, and you can come up with a single value, and that may be an interesting thing for you. And by this is called, the idea is called one class one convolution. And using this kind of convolution, what happens, that at the later point of time, if you want to apply any kind of computation, you need not to consider all the items, only single, considering single item is sufficient to find out the output. So using this kind of idea, it was able to reduce the computation, and even with the larger number of layers, it was, if it has a lesser number of computation, and you can train this particular model. Very interesting idea. And because it was seeing the things on the different perspective, the error rate from 7.3 reduced to 6.7%. So this was a ultimate thing, because now you have seen that very good kind of architecture we have achieved. So we can be going on with this particular kind of architecture. Then came a very different kind of idea, and the idea was this, that that actually you also do most of the time. So for example, let's assume there is some problem, and for this much number of layer is sufficient. Okay, there is a problem for which let's assume that this much number of layer is sufficient. Okay, so if I ask you that, do you know that how many layer is needed? You given a problem, do you know that how many layers are needed? No, you have to do multiple experiment, then only you would know. You don't know that how many layers are needed. So the idea was this sense that okay, let's assume that it is a 20 layer that is good to go. Okay, but I don't know 20. So who is stopping me to put a 50 layers? If I put 50 layer, if because ultimately learning is done by whom? Learning is done by the computer. I am telling that use 50 layers, and the right parameter can be obtained by the computer, because I would deploy the uh, gradient descent based method, and I would ask from that system that find out the right parameter for me. So the system would do whatever he can do, and he would come up with the right kind of architecture, right kind of parameter that works for me. So why, if my problem needs 20 layers, and if I deploy 50 layers, I may safely assume that system, if the system can learn, he would learn right parameter here, and these things are going to connect one. They are everything whatever is there, they can pass everything to the next layer, and by this what would happen, that whatever output being computed into this particular place is same going to be available at the output. So my task is done, my task would be done. I can always think, for example, if you go to the market and you want to, for example, purchase want to get a toffee of 10 rupee. If you have 20 rupees, what is the problem? 10 rupees you can pay, always you can pay, and some money is left with you, so you can solve your problem. The same idea is this, that you, if 20 20 works, then I'm going to deploy 50, and I would ask my computer to actually work hard to find out the right parameter. System would definitely try to find out the right parameter, and it will solve my problem. Make sense? Very simple idea, very simple idea. But actually, this is a philosophical level very good proposal, and the proposal is called the no, no, this proposal is not called ResNet. This was a very good proposal. Okay, but what happens actually, that actually this should work. Are you, do you think that this should work? Yes or no? How many of you think that it would work? Should it work or not? I am telling that if my system need 20 layers, I am going to put 50 layer. Will this work or not? Yes or no? Hmm? Yes or no? Rohit, Mohit, Srijan? It should work, because if if my problem is such that it requires 20 layers, but I am putting 50 layers, then my network must work. Okay, but actually what happens, that how the system is learning this particular weight? System is learning because of what? Abhijit sir is writing, training will become difficult and learning will be slow. Okay, I agree with that, but right now let's assume that I'm not thinking about that, because if we want to make it very good, then we have to invest our brain, na? And we are not sure about this, that what is the right thing. So maybe we would also spend more time to searching right parameter for the network, and that's why system is not learning in that particular time. So system is going to ultimately the things are going to be delayed, because I don't have the right architecture to go ahead. So I would sitting and thinking, and by this I'm wasting my time. And anyway, if somebody want to do the things better, he have to invest more money, because getting more computation is just investment, can be directly reflected to the that give me more money to find out this computation. Okay, in that sense it must work. But actually the issue is this, that how the system find out the right parameter using gradient descent. And using gradient descent, the things which are actually nearby, they should also work good. But in this in this setting which actually I am in, if my network works best with the 20 layers, and here the things which are actually going to be multiplied, if they are not one, what would happen? would my system be doing good thing? No, my system would be not be giving me the right thing. My system would not be performing good, because I need, because after 20 layers what I want everywhere to be 1. So you know that if even if the possible values are into 0 and 1 only, so and I want to find out a particular value, maybe 0.5, the probability of hitting that value is actually 0, because anything that is nearby is actually now they are not going to work. So gradient descent based method are actually not going to work into this kind of setting where actually I am going to find out 1 and the nearby things are not working. So this was a good idea, but actually this idea could not work because of this kind of restrictions only. So there was a then the actually researchers have actually introduced a kind of concept. This is called the skip connection, and they told that after, because what was the problem, that the nearby things were not working. So they told that I would be using some kind of skip connection. Some previous values are also I am going to connect with this particular value. So what happens that even if I so then what happens that I need the summation of two values to be 1. Summation of two values, for example, what is the current value at this particular weight plus what was the something is coming from previous thing, and the summation of those things should be 1. So this I can adjust, because even if this value is not 1, I can adjust this value, because this value is coming from the previous thing where I can apply the gradient descent and I can find out the right value of that particular quantity, so that the summation becomes 1. So these things would come into the more detail into the later classes. So I just wanted to tell you that using this kind of idea where uh, where the idea was this, that I would deploy so many layers. So they were only thinking about 22. Somebody come and he told that I'm going to deploy 152 layers. See how big network he wanted to train. So ResNet is another idea that has 152 layers and even more layers they can apply. However, you know that training these kind of network is not possible for everybody. So the train parameter people mostly use. So ResNet is another idea. The error of ResNet reduced to 3.6%, and it is in now it becomes better than the humans. So anything which becomes better than the humans, most probably we don't want to go forward out of that, because we think that now it does, maybe the system is overfitting, because who is providing the right labels? Ultimately the humans are providing the right labels, and you are becoming better than the human with the help of human doesn't make much sense. So around 2017, the best accuracy that was actually achieved by the AutoML kind of Google algorithm that achieved 2.25%. They are not much that much discussed, because only of simply this particular region, that they are going to be better than they are better than the human. Maybe that may not be needed to be achieved. Ensemble of techniques actually says that I am going to use multiple techniques at the same time. So and then using some kind of a fusion of those kind of results and to come up with the right kind of results. SENet and the AutoML kind of results actually improve this thing to even further. So this is some of the story that how the things actually forwarded into the domain of deep learning and into the computer vision and solve very important computer vision problem. You may be thinking that what is the basis that why having multiple number of layers is going to solve my problem, why it is going to solve my problem. So the idea is this, that our human vision system is also hierarchical. Okay, so when we our eyes something sees something, so it creates some kind of feature which is called the v1 kind of feature. Then using them we try to generate v2 feature, and that is used to generate v4 features and it posterior, it anterior. So I'm not much expert of this, but the overall idea is this, that our brain also does the processing into the similar way, where it uses the previous thing and some of the conclusions out of that to the next layer, and this particular layer does not see that what is happening or directly happening over here, but only consolidate whatever things are before that. Having the image is having the image, because you know that this is this image, this is the image, and you can see that only numbers are there. You cannot visualize that what does it mean. But if you, our visual system actually can only give us some kind of idea that what is there. So for the computer it is very difficult thing, very difficult game when it wanted to tell that what is inside the things. You know that we have discussed that there in a given image there could be occlusion, means some part is not visible, viewpoint variation, scale variation, small and big things, illumination variations, deformations, background clutter, noise, interclass variation, and much more. Many things could be there inside the image. So this particular kind of things become difficult. Using the deep learning means using multiple number of layers, we can create the hierarchy of the feature, and this actually is very useful to create some right kind of features for us. So whatever you provide to the system, for example, when you provide an image to the system, so first layer actually does kind of transformation. So you can see that, you can think that there is some function that is being applied and you get some version of that. Then next layer again apply some kind of function. Next layer again apply some kind of function. So at the end, whatever you are going to get is actually a big non-linear deformation of the thing that actually you have fed into the system. You may also think that, as we have discussed earlier also, that you may think that the first part could be the shift, second part could be maybe the k-means, next part could be the feature pooling, next part could be the classifier. So different kind of things you are one by one applying, and at the end you are going to find out that what is the what is the what is the thing that is inside this particular image. Uh, this is again a very simple kind of illustration that wanted to be provided to you. That let's assume that you have an image. So very basic level, what you see, that you see that what are the pixels, okay, what are the pixel values. So pixel values actually correspond to the color only, that what is the color over there. Then you combine them and see nearby things and try to come up, looks like that what is the gradient, what is the color gradient in one side. Using the color gradient you can come up to the understanding that it looks like that this is a small part and this is a small portion of the things. Using small portions you can compute the maybe some part of that. For example, if you want to build a car, you come up that looks like that there is a tire, there is a horn, there is something, some different kind of parts you can come up into the next layer, and out of that you can develop a classifier that can tell that if there are hand and head, then it is a person. If there is a steering and there is a tire, then it is a car, like that. So higher means multiple layers. When you have, these are the different layers, multiple layers you have, so they are going to have the different kind of representation of the same data. This is a very interesting paper that came out around 2014, ECCV 2014 paper, visualizing and understanding the CNN, that actually tried to develop a CNN based 5-layer CNN based structure and try to show that what actually means that when you are going to have the feature. So at the first level, whatever being learned, if you try to translate them, they only translate to the only pixel intensity. Okay. At the second layer, these kind of features are there. They translate to some of the parts. You can see that what you can, how you can associate with them. Do you get any idea that what is over there? At the layer 3, you see some structures coming up. You can see that some of the structures are going to come, and then with respect to that, you can also see that looks like that there is some tires somewhere into the flower. There are some petals are coming in some architecture, some of the structures are coming. So you can see that with the humans, you see that different kind of things are coming. So this is the layer 3. What is happening on the layer 4? So these kind of features are coming again with respect to every class. It is going to show that. So here you can see that more things are actually getting combined. Okay, more parts are getting combined, and then a bigger kind of architecture, you can see that it is going to come. Final layer is going to give you the final thing, means it is combining, and ultimately it is going to produce the complete thing out of that. Make sense? So that's all. That's all for today. So I wanted to tell you that multiple layers which you are going to use, they are going to have the different representation of the previous layer by combining a different previous thing. They are going to make the hierarchy of the features, and that's why at the end you are going to get what is the final thing. Thank you very much. Thank you for joining this session.